Assalamu alaikum students. Today we are going to start lecture number 38. The course we are studying is Classical Mechanics PHY 509 for BS 5th semester. The topic we are going to discuss is tensors. The topic is under the kinematics of rigid body. As the objects tend to rotate, they involve the three rotational axes and there is change in their axis as you studied in the Euler's angle and Euler's equation under kinematics and the rotation of the rigid body. To discuss and understand tensors, we're going to start with the scalars, vectors, and then tensors. A scalar is a physical quantity that is represented by a dimensional number and a particular point in space and time, which has a magnitude but not a direction. Examples are hydrostatic pressure and temperature. And a vector is a bookkeeping tool to keep track of two pieces of information, typically the magnitude and the direction, for a physical quantity. Examples are position, force, and velocity. The vector has three components. You know that it is a vector, so it has three components. Vector v velocity is equal to v1 x1 plus v2 x2 plus v3 x3. So for the three components designation, we will write summation I vi xi, or in the vector form, vector mod form, we can write v1, v2, and v3. Here you can see the velocity vector in three coordinates x1, x2 and x3. Here you can say x1 is the x coordinate, x2 is the y coordinate, and x3 is the z coordinate, and the v vector lies in the three axes x1, x2 and x3. That is the velocity vector shown in the figure. The magnitude of the velocity is a scalar, as v is equivalent to v vector of mod v vector mod. What happens when we need to keep track of three pieces of information, uh, as that vector is inside the or between the three coordinates, so the magnitude is known but the specific direction we have to track. So we need to keep the track of three pieces of information in our consideration. Three kinds of information for a physical quantity. So as that three coordinates are involved, so for that physical quantity we need a tensor. Examples are stress and strain. The tensor has 9 components. So the stress tensor is written as sigma ij, where I and j are the components uh, of the tensor. Sigma 11, sigma 12 as x coordinate and xx coordinate, xy coordinate, xz coordinate, and similarly yx, yy, yz. So we can write sigma 11, sigma 12, sigma 13, sigma 21, sigma 22, sigma 23, and sigma 31, sigma 32, sigma 33 for the three coordinates in a mod form, that is a tensor. For stress, we keep track of magnitude, direction, and which plane the component acts on. As a stress is a vector quantity, so we need to track the magnitude, direction, and in which plane the components act on. We have to keep knowing about that plane as well.
Everyone knows the terms vector and scalar quantities, but engineers also come across another term known as tensors. Today we will try to understand what a tensor is. Let's consider a Cartesian coordinate system. So each direction of the coordinate system comes with coordinate basis vectors or unit vectors. As the name suggests, they have a length of 1 of whatever the main vector is and direction in the direction of respective coordinate axis. So I hat shows the unit vector in x direction, j hat shows the unit vector in y direction, and k hat shows the unit vector in z direction. Now we can find the components of our vector. Let's consider a vector capital V in the xy plane. In order to find the y component, we will project the vector capital V on the y-axis, and similarly for x component. If we put a beam of light perpendicular to y-axis on the vector V, we will see the projection or the shadow of the vector v falling on the y-axis. Now, if we line the y direction unit vectors along the y-axis on the projected length OA, we can find the component y of the vector v. Similarly, if we line the x direction unit vectors along the x-axis on the projected length OC, we can find the x component of vector v. So, we can write the vector v as 4i hat plus 5j hat plus 0k hat. That represents the vector capital V. We can find the magnitude of the vector capital V as square root of the sum of the squares of the x and y component. And the direction of the vector capital V as tan inverse of y by x component. Also, we can write it in a matrix form, which we commonly call it as column vector. So, we can generalize the vector capital V as Vx plus Vy plus Vz. Notice each component requires only one index because there is only one directional indicator or basis vector per component. This is what makes vectors tensors of rank 1, one index or one basis vector per component. So scalars can be said as tensors of rank 0 because scalars have no direction indicators, so no basis vectors required. Now we will see a tensor in three-dimensional space, that is stress tensor. Stress, as we know, is given by force divided by area. If we take a cubical solid element, we can see a stress component sigma xx, which is normal to the surface in x direction. So this is known as normal stress. As you can see, it has two subindex, so it has two basis vectors in x direction. There is another component tau xz, which is the shear stress having two basis vectors in x and z direction. Tau xy, which is the shear stress having two basis vectors in x and y direction. Similarly, in y and z axis, each will have three components of stresses. So there are 9 components of stress, which include 3 normal stress components and 6 shear stress components. As you can see, each of these components have two basis vectors, so this is called a tensor of rank 2. Why would someone need this kind of arrangement? Let's say if we have a solid body and we want to find stresses in every possible direction combination, we would need something like this. Like sigma xx shows the x directed force on the surface area whose area vector is in the x direction. Similarly, tau xy shows the x directed force on the surface whose area vector is in the y direction, and so forth. So a tensor is an algebraic object that describes a relationship between the sets of algebraic objects related to a space vector. Like you see here, the stress tensor is basically a combination of 9 different stress components which are related in a vector space.
First attempt at a definition for tensors, I'll just read it off. So a tensor is a multi-dimensional array of numbers. And by array, I basically just mean grid. So a grid of numbers. Okay, so let's see some examples of what this might look like. So the simplest example of a tensor is what we would call a scalar, or sometimes a rank 0 tensor. And a scalar is basically just a number, so any number like 1, 2, 5, 3/4, pi. These are all examples of scalars. And we don't normally write scalars as arrays, but if we wanted to, we could write little square brackets around the scalar like this and sort of pretend it's an array, but we don't normally do that. Alright, so those are scalars. Another example of a tensor you've hopefully seen before is a vector, or a rank 1 tensor. And we call it a rank 1 tensor because it's a list of numbers that extends downward in one dimension. So it's like a one-dimensional array. So that's a vector. Another example you've probably heard of are matrices, or rank 2 tensors, and we call them rank 2 because they are a two-dimensional grid of numbers, so they extend up, down, left to right. And if you recall from the last video, I mentioned that the metric tensor from general relativity is a rank 2 tensor. And these little Greek letters that you see here actually stand for numbers that represent the row and column of the particular entry of the matrix that we're talking about. So the metric tensor is really just a matrix. And we can go higher and higher. This is a rank 3 tensor because it's in a three-dimensional grid of numbers, sort of arranged in a cube. And we can go on and on, rank 4, 5, 6, as high as we want. So any multidimensional array of numbers is a tensor. So I call this the array definition of tensors. Okay, so I said that this was a first attempt at a definition, and it does give us some idea of what a tensor is, but this definition is actually wrong, and here's why. So tensors can be represented as multidimensional arrays, but that's not what they fundamentally are. Tensors aren't just a bunch of numbers that we toss together. Tensors actually have real geometrical meaning. And if we just think of tensors as these multidimensional arrays, we sort of miss out on the geometrical meaning behind them. So if we casually toss the word tensor around to mean a multidimensional array of numbers, that's sort of fine. There's nothing wrong with that. But if we're thinking seriously like mathematicians and we want to understand geometry, this definition, the array definition, is simply just wrong. So it's no good to us. Okay, so let's try again. So here's another attempt at a definition. I'll just read it. A tensor is an object that is invariant under a change of coordinates and has components that change in a special predictable way under a change of coordinates. Okay, so that's certainly a mouthful. So what does that mean? So let's start with the top part. What does it mean to be invariant under a change of coordinates? Well, to explain that, I'd like you to try picking up a pencil and point the pencil toward the nearest door that you can see. So there are a few things that we can say about this pencil that are just facts, and they don't depend on any coordinate system. So for example, the length of the pencil, the length won't depend on our choice of coordinate system. The length is an intrinsic or invariant quantity. Also, this pencil is pointing toward the door, and that's just a fact. It doesn't depend on what coordinate system we use. The pencil's orientation is intrinsic or invariant under the choice of coordinate system. Now, the second part, what does it mean for components to transform predictably under a change of coordinates? Well, to start off, let's introduce a coordinate system here. So we have a nice 3D coordinate system with 3 vectors here that give us the main coordinate directions. And what we can do is we can measure the pencil using this coordinate system. All right, so it looks like this pencil is made up of 2 yellow arrows, 1 green arrow, and then 2 blue arrows. All right, so we can write this pencil as a linear combination of the coordinate vectors here. Okay, so what we just did here by breaking down the pencil into the coordinate vectors is we measured the pencil's components. The components are just the amount of each coordinate vector that we need to construct the pencil, right? So with this coordinate system, the components are 2, 1, 2. Now, I introduced this coordinate system here, and you might think it's a pretty sensible coordinate system because all the direction vectors are the same length and they're all perpendicular to each other, so that's kind of nice. But really, there's nothing special about this coordinate system, right? I could just as easily introduce another coordinate system like this, where the vectors are all different lengths and they all sit at weird angles relative to each other. But mathematically, neither of these is more correct than another. They're simply just different choices. And so with this second coordinate system, I can sort of do the same thing. I can measure the pencil along each coordinate vector, and I can see that this pencil is made up of 2 black vectors, 3 purple vectors, and then 1 red vector. And again, I can write the pencil as a linear combination of these vectors, and I get the components 1, 3, 2. So you'll notice when I measure the pencil using different coordinate systems, I actually get different components, right? And this is a really important idea. The pencil's components are not invariant, right? They change depending on the coordinate system they use. Okay, so the pencil is invariant, but the coordinates are not invariant. Okay, and again, that's a very important idea. So now it turns out that if we know how to change one coordinate system into another coordinate system, right? So if we know how to go back and forth between these two coordinate systems, then we should also be able to figure out how to change back and forth between these different sets of components. And this process of going back and forth between coordinate systems and components, that's what I'm going to call forward and backward transformations. And I'm going to talk about those in the next video. All right, so backing up, what a tensor is an object that is invariant. It doesn't depend on the coordinate system, but its components, which do depend on the coordinate system, change in some special predictable way that we can figure out using these forward and backward transformations. And this is what I'm going to call the coordinate definition of a tensor. And this definition is actually pretty good. It does get to what the heart of a tensor is. It's an object that's invariant, but whose components change. But it turns out that we can come up with an even better definition. And so I'm going to switch to that one here. So here's our third final definition. I'm just going to read it off. A tensor is a collection of vectors and covectors combined together using the tensor product. So this definition ends up being really nice. It's really short and sweet. There's just one problem. If you've never studied tensors before, you may have heard of vectors, but you've probably never heard of a covector, and you've probably never heard of the tensor product. So the downside of this definition is that we need to put in a little bit of work before we can even understand what it means. But once we understand what all these things mean, it's actually a really simple definition. Tensors are just vectors and covectors combined together in different ways using this thing called the tensor product. So this is what I call the abstract definition of a tensor. So this is really the best definition of a tensor we can come up with, and I'll get to this definition later on in the video series once we have the basics down. All right, and I have a little bonus part here. So for those who do have a calculus background, I'm going to talk about how tensors pop up in calculus. And that's when we see tensors as partial derivatives and gradients that transform with the Jacobian matrix.
Now, to understand the stress tensor, to understand the tensor, we have to start with the stress tensor to understand. As we know that stress tensor is written as sigma ij is equal to mod of matrix of sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, sigma 3 2, and sigma 3 3. The first subscript keeps track of the plane of the component acts on described by its unit normal vector, while the second subscript means that I keeps the track of the plane the components act on, and the second subscript j keeps track of the direction. The first component I designate the plane on which the uh, components is acting, and while the second tells that in which direction. Each component represents a magnitude for that particular plane and direction. So each component means that sigma 1 1 or sigma 2 1, that each component represents a magnitude for the particular plane and direction. So sigma 1 1 shows the particular magnitude and particular plane direction, plane and direction. That means particular magnitude in x direction and particular plane of x and particular plane direction in x direction. Now you can see a figure that we have x, y, and z coordinates. It means x1, x2, and x3, and so we see that the x direction plane is sigma 1 1, and along the z direction plane vertically is sigma 3 2, that z and y are involved, and in the z direction the plane is along the x3 3 direction. So as we can see that the normal out of the plane is sigma 2 1, sigma 1 1, and so on for all uh, four of the 9 components of the stress tensor are shown acting on the small cubic fluid, that is sigma 1 1, sigma 2 1, sigma 32 and sigma 33. So we can say that the stress tensor is always symmetric. So we can say sigma ij is equal to sigma ji. Thus there are only 6 independent components of this stress tensor, which of 3 are the symmetric and remaining are the 6 components which are the independent components. Now to explain the stress tensor, we have an example of simple shear stress, that is written as sigma 1 2 is equal to sigma 2 1, that is the symmetric form of the tensor, that is equivalent to sigma, and that shear stress is equal to partial is equal to F over A, force per unit area, given by equation number 27, and sigma 1 3 is equal to sigma 3 1, and that is equal to sigma 3 2, and that is equal to sigma 2 3. So all the components are equal and opposite, so that is equal to 0. That is written in equation number 28. So we can write that sigma ij is equal to sigma 1 1. At the place of sigma 1 2 we write sigma, and at the place of sigma 1 3 we write 0. At the place of sigma 2 1 we write sigma. At sigma 2 2 written as it is. At sigma 2 3 we write 0. At sigma 3 1 we write 0. At sigma 3 2 we write 0, and at sigma 3 3 written as it is. Now we have an example of a simple extension, that sigma ij is equal to matrix sigma 1 1 0 0 0 sigma 2 2 0 0 0 sigma 3 3. That is equation number 30. Now for the example of the hydrostatic pressure, we write for sigma 1 1 we write minus p, for sigma 2 2 we write minus p, and sigma 3 3 we write minus 3. The minus sign is because pressure compresses the fluid element. Polymers and the most liquids are nearly incompressible. For an incompressible fluid, the hydrostatic pressure does not affect any properties. For this reason only, differences in the normal stress are important. In simple shear, the first and the second normal stress differences are the differences are n1 equivalent to sigma 1 1 minus sigma 2 2, that is equation number 32, and sigma n2 equivalent to sigma 2 2 minus sigma 3 3, that is equation 33. The extra stress tensor defines tau ij equivalent to sigma ij plus p for I is equal to j, and sigma ij for I is not equal to j. Stress and strain rate tensors. Strain is a dimensionless measure of the local deformation. As you know that strain has no unit. Since we want to relate it to the stress tensor, we had best define the strain tensor to be symmetric. Now we have to relate the stress with the strain tensor, which is symmetric, and strain is a dimensionless quantity. It is related to the deformation only. So we write sigma ij gamma ij into t1 comma t2 equivalent to partial ui into t2 divided by partial xj into t1 plus partial uj t2 or partial xi t1, that is equation number 37, as the u vector is equal to u1 x1 plus u2 x2 plus u3 x3 is the displacement vector of the fluid element at the time t2 relative to its position at time t1. So here we have the displacement vectors for the two fluid elements A and B, and we write for the from the origin to the point A, that the vector xa t1 for the point A for the time t2 is xa time t2. From point A to B on the left is del x into t1, and from point A to B is del x t2 in time t2. So the displacement between point A and A prime is u a t2, and the distance between point B and B is u b t2. The strain rate tensor or rate of deformation tensor is the time derivative of the strain tensor. So we can write gamma ij dot equivalent to d gamma ij over dt. That is equation number 38. The components of the local velocity are vi is equal to d ui over dt. That is equation number 39. Since the coordinate xi and time are independent variables, so we can switch the orders of differential. Gamma dot ij is equivalent to partial vi over partial xj plus partial vj over partial xi. That is equation number 40. Now, for the stress and strain rate tensors, we have a simple example of simple shear. We write gamma ij, that is equivalent to matrix 0 gamma 0 gamma 0 0 0 0 0 0, where the scalar gamma is equal to partial u1 over partial x2 plus partial u over partial x1 is equation number 14. So its derivative is written as gamma ij is equal to matrix 0 gamma dot 0 gamma dot 0 0 0 0 0, that is equation number 51, where the scalar gamma dot is equal to d gamma over dt. Now to simply extend the example, gamma ij is equal to 2 epsilon 0 0 0 minus epsilon 0 0 0 0 minus epsilon, that is equation number 47, where the scalar epsilon is equivalent to minus u1 over partial x1. For gamma ij dot is equal to matrix 2 epsilon dot 0 0 0 minus epsilon dot 0 0 0 minus epsilon dot, where the scalar epsilon dot is equivalent to d epsilon over dt. That is equation number.
So today let's discuss the stress tensor. Let's take a block of material and pull on both ends with a load P. Now if we assume this is a solid, you might expect the response of material to be something like that. You might elongate, get a little bit longer in this direction, a little bit thinner in that direction. Now if we took the same material and applied the same force, but we applied it to that face, the top and the bottom face, we might expect the response to look something as such. So not only does the magnitude of the force matter, because obviously if I pulled on this harder it might elongate more, but the face upon which that force acts is important. So this leads us to the idea of the stress tensor. So the stress tensor is just a generic representation of the state of stress inside the material. So if we have a cube, we have faces in different directions, and the stress tensor just describes the forces or the stresses that are acting on each of those faces. So in an XYZ coordinate system, we have faces which have normal directions pointing in the X, Y, and Z direction. On each of those faces, we have X, Y, and Z forces. So the notation, the first index, X, denotes the direction of the normal vectors. So X, X, X are all ones acting on this face. Y, Y, Y are all ones acting on this face. And the second one is the direction of the force. So X, X is the X force acting on the face with the normal component in the X direction. So we represent these 9 components of the stress tensor in a matrix. So we represent it as such. So it has 9 components, and this is what we call the stress tensor. So we've seen before, we had scalar quantities, things like temperature, pressure, density. These are just a single number, one number, so these can change with time and space, but at a particular point, at a particular time, it's just a number. Vectors were things like velocity and heat flux. These have 3 numbers, right? The x, y, and z components of the vector, right? Because velocity has a magnitude and a direction. Tensor is things like stress. Like with a vector, I usually put an arrow over it. When I'm writing to denote a tensor, I'll usually put 2 lines in it just to remind myself that it's a tensor, and it's described by 9 numbers, or a 3 by 3 matrix. So there's our tensor. Now if we want to find the stress vector on any surface, all we have to do is take our stress tensor and take the dot product with the normal vector. So again, the arrows are vectors, the two lines is a tensor, and if I take the dot product of a vector with a tensor, I get back a vector. Now the way I usually remember this is just write things out as sort of a vector matrix multiply. So if we write our normal vector as a column vector, and I take the vector matrix product of this vector n dotted with this matrix T, then that gives me a vector which is the stress vector. So as an example of this, let's just consider a face where the normal vector points out here, just to make sure that this works. So my normal vector there is 1, 0, 0. And if I do the vector matrix multiply, I simply get a vector which has components x, y, and z components, which we just extract the values of this from the stress tensor off that face. So it's kind of a trivial example, but we see we get the right result. And if I use the normal vector 0, 1, 0 or 0, 0, 1, I simply extract either the x, y, or z row. And again, these rows are all the forces or stresses that are acting on a face with a normal vector pointing the x direction, y direction, z direction. Now let's consider a slightly more complicated example. Let's look at a surface whose inclined at 30 degrees. So therefore the normal vector is 1/2 square root of 3 over 2 and 0. So let's just write this out. So we get a vector where the x, y, and z components are starting to mix the values from the stress tensor, which are acting on the x face and the y face. And you can see that since our normal vector is closer to the y normal vector, we're sort of weighting those stresses more by a factor of square root of 3 over 2 than the ones that are pointing in the x direction. And as this angle changes and this becomes closer to 1, we see we start to pick up more the components that are acting on that y face, the ones that are acting up there on that y face. So let's see how we might use the stress tensor in our formulation for fluid mechanics. So if we have our arbitrary volume, a potato, and if we imagine everywhere along the surface of this thing, we can go to a point and we can define a stress vector. So this is the force per unit area that's kind of acting locally at that point. And for whatever reason, it could be different all over the object, so it just sort of changes as we go around. If we want to find the total force due to these surface forces, so it would be a vector, all we would have to do is integrate that stress vector, if we somehow by magic knew it, over the surface. And if I sum up all those little forces all over the surface, I get a net force. So again, this is a stress, which is a force per unit area. So I integrate over the area and I get the net force. But we know this stress vector is related to the stress tensor. So I can replace the stress vector within the normal vector, right? The normal vector which points everywhere out of our surface, dotted with the stress tensor at that point. Now I won't prove it, but the divergence theorem works just as well for tensors as it does for vectors. So this can be written as the divergence of the stress tensor integrated over the volume. So this is going to be a key result that we're going to use. And if we want to know how to calculate the divergence of the stress tensor, well, if we remember this gradient operator, the del operator, right? If we just write it out as a vector, we can do exactly the same thing when we looked at dotting a tensor with a normal vector. So I'll write out the x, y, and z component of my del operator. And if I just simply do my vector matrix operation, I get obtain the following vector that has x, y, and z components. And you can see the form there. So when I take the divergence of a tensor, I get a vector, and it has this form where I'm taking the gradient and the x, y, and z direction of all these different 9 numbers. So taking the divergence of a tensor gives me a vector which has this form. Let's see if we can prescribe some physical meaning to the divergence of the stress tensor. So let's go back to our cube. So there's our cube in x, y, z. I'm going to place the origin of this cube at the back corner there. And now let's just draw the x forces. So let's just consider the x forces. Each face of this cube we're going to have some force, but we're going to consider it to be sort of finite in size, and then we'll take the limit as that size goes to 0. So there's delta x, delta z, delta y. So each side is going to have length. So each face of this has, all 6 faces of this cube have stresses. So on this back face, we'll just call that Txx. And on this front face, we're going to have a stress as well, pointing in this direction, sort of outward from the surface. And if our stress tensor is varying in space, but over a small distance, we can approximate the stress here as Txx, the value that it was at 0, 0, plus a little bit, based on its derivative with respect to x, times the length delta x. So that's just the Taylor series. Now we're only doing x forces only, so I won't draw the others, just so this diagram doesn't get cluttered. Now let's do the forces acting on the 2 faces that have normal directions in the y. So we'll start at the bottom. That one will be pointing backwards. That is Tyx. And this one will be pointing that way. And likewise, if the stress tensor is not constant in space, it's going to be given by the value here at 0, 0, right? Plus a little bit based on its gradient in the direction y. And then we're going to have likewise for z. And now it's getting a little more cluttered to draw, but I'll draw it anyway. And so there are forces, all of them, right? So we have 2 that are acting on the z face, 2 that are acting on the x face, and 2 that are acting on the y face. So let's just sum all those up. Let's sum the forces. So we'll start with the blue ones. We have Txx plus the small change from here to there, minus the force that's pointing backwards. And these Txx, these are stresses, so in order to get forces, I have to multiply it by delta y and delta z. Now let's add the other ones in. So there is the sum of the forces. Now we can see several things cancel here. And what we're left with is that the force in the x direction is the first component, what we calculate on the last page when we did the divergence of the stress tensor. So that first component is the net force in the x direction times the volume. So we can think of the divergence of the stress tensor as the net force per unit volume.
48. Now to understand for the Newtonian fluid, for the tensors, the Newton's law is written in terms of the extra stress tensor is tau ij is equal to eta gamma ij dot. Equation 49 is valid for all components of extra stress tensor in any flow of Newtonian fluid. All low molar mass liquids are Newtonian, such as water and benzene. Now this simple shear example is gamma ij dot is equal to matrix 0 gamma dot 0 gamma dot 0 0 0 0 0, that is equation number 48. Now gamma so now shear strain tensor is tau ij is equal to 0 eta gamma dot 0 eta gamma dot 0 0 0 0 0, that is equation number 48. The normal components are also 0, so sigma 1 1 and sigma 2 2 and sigma 3 3 are also 0, that is equation number 53. And the normal stress differences are such thus both 0 for the Newtonian fluid. So we can write n1 is equal to n2 is equal to 0. Now for the simple extension, we write gamma ij dot is equal to matrix to epsilon dot 0 0 0 minus epsilon dot 0 0 0 0 minus epsilon dot, that is question number 48, and for tau ij, that is theta, into matrix to epsilon naught epsilon dot 0 0 0 minus epsilon dot 0 0 0 minus epsilon dot, that is question number 55. As from the figure, you can see the three coordinates x, y, z and the components vx, vy, and vz for the velocity vector v. So the velocity is v is equal to vx I cap plus vy j cap plus vz k cap. I, j and k are the unit vectors in the x, y, and z direction. X is in the direction of x, I dot, j dot is vertically upward, and k is along the z axis. Acceleration is a is equal to dp over dt. So its components are ax I cap plus a by j cap plus az k cap. A is equal to dv over dt in work vectors, so it represents three equations: ax dvx over dt, ay is equal to dvy over dt, and az is equal to dvz over dt. So we can write for the acceleration a is equal to dvx over dt I cap plus dvy over dt j cap plus dvz over dt k cap. The vector is simply notation bookkeeping, so divergence n is written as del dot v equivalent to partial vx over x partial x plus partial vy over partial y plus partial vz over partial vz if partial vx or partial x is greater than 0 and partial yv over partial y is greater than 0 and partial vz over partial z is greater than 0 and vx is greater than 0 and vy is greater than 0 and vz is equal to 0, then you have an explosion, the name divergence. Now for the vector calculus, we have the gradient del operator p equivalent to partial p or partial x, where p is a scalar quantity I cap plus partial p over partial y j cap plus partial p over partial z k cap. 3D analog of a derivative. Gradient operator makes a vector from the scalar p, whereas divergence makes a scalar from the vector v. And gradient is made when the when the operator is applied on a scalar, and whereas the divergence is made when a scalar is got from the vector, as the two vectors are taken a dot product, so that we get the divergence. And Laplacian is partial del square v equivalent to partial square vx or partial x square plus partial square vy over partial y square plus partial square vz or partial z square. So we can write del square v is equal to partial square vx or partial x square plus partial square vx over partial y square plus partial square vz over partial z square into I cap. All the x component of v and then all the y components on the v above, then j cap plus partial square vz or partial x square partial square vz or partial y square plus partial square vz or partial z square k cap. Laplacian operator makes a vector from a the vector v, also written as del operator dot del operator into v, divergence of the gradient of the v. We get the we first we find the gradient of v, then we apply the divergence of the v in the resultant. So we can write del square v is equal to partial square vx or partial x square plus partial square vx over partial y square plus partial square vz over partial z square into I cap. All the x component of v and then all the y components on the v above, then j cap plus partial square vz or partial x square partial square vz or partial y square plus partial square vz or partial z square k cap. Laplacian operator makes a vector from a the vector v, also written as del operator dot del operator into v, divergence of the gradient of the v. We get the we first we find the gradient of v, then we apply the divergence of the v in the resultant. Now to understand the conservation of mass in a fluid, the equation of continuity is given as: consider a control volume having a unit vector and normal up out of the that surface Rho is density scalar, v is a velocity vector, n is a normal vector on a surface, and rho into v dot n into dA is the net flux out of the control volume through the small area dA. So we can write integral s rho into v dot n dA is equal to net flow rate mass per unit time of the control volume. Integral v rho dv is total mass inside the control volume, and dO dt into integral v rho dv is the rate of accumulation of mass inside the control volume. Mass balance is equal to d by dt integral v rho dv is equal to minus integral s rho into v dot n into dA. Conservation of mass in a fluid. Point 2. We write d by dt integral v rho dv is equal to minus integral s rho v dot n into dA. Now the integral mass balance can be written as a differential equation using the divergence theorem, that is integral s rho dv and v dot n dA is equal to integral v del dot into rho v dv. So we can write integral v rho partial rho over partial t plus del dot into the rho v into dv, that is equal to 0. Control volume was chosen arbitrarily, that is partial where partial rho over partial t plus operator del operator dot into rho v, that is equal to 0. Derived for a derived for a control volume but applicable to any point in space. That equation lastly described derived from the for the control volumes and applicable to the points in this space. Now, quantum mechanics applies for both gas and liquid. Conservation of mass in a liquid. A liquid is incompressible. Density rho is always the same, so partial rho partial t is equal to 0. Rho is equal to constant. Integral mass balance gives d by dt integral v dv is equal to minus integral s rho into v dot n dA becomes integral s into v dot n dA is equal to 0. As we know that the equation of continuity is written as partial rho partial t plus del operator dot into rho v, that is equal to 0. So del dot v is equal to 0 for becomes del dot v is equal to 0 for incompressible liquids in Cartesian coordinates. So for the v vector with the all components, and partial vx or partial x partial vy or partial vy plus partial vz or partial z is equal to 0. Now to discuss the incompressible continuity equation of the liquids, Cartesian coordinates x, y, z, partial vx or partial x, partial vy or partial y plus partial vz or partial z is equal to 0. And in cylindrical coordinates, we write for the r, theta and z, 1 over r into partial over partial r, vr plus 1 over r into partial v theta or partial theta plus partial vz or partial z is equal to 0. Spherical coordinates r, theta and phi. Cylindrical coordinates are theta z in the 1 over r partial over r r vr plus 1 over r partial v theta or partial theta plus partial vz or partial z is equal to 0, and the spherical coordinates are theta by phi 1 over r square partial over partial r square vr plus 1 over r sin theta partial over partial theta v theta sin theta plus 1 over r sin theta partial v phi over partial phi is equal to 0. All are simply the del dot v is equal to 0. Cylindrical coordinates are theta z in the 1 over r partial over r vr plus 1 over r partial v theta or partial theta plus partial vz or partial z is equal to 0, and the spherical coordinates are theta by phi 1 over r square partial over partial r square vr plus 1 over r sin theta partial over partial theta v theta sin theta plus 1 over r sin theta partial v phi over partial phi is equal to 0. All are simply the del dot v is equal to 0. In the last, these are the references for the following of the subject and topic. If there is any kind of difficulty regarding the topic, you can use the references of the books. Thank you. Now today's topic is tensors is completed here. If has any kind of question, you can ask me in the physical class. We will surely discuss. Thank you. Allah Hafiz.